to plating and coating your fasteners for cost and performance. My name is Kelly Charles. I'm an NFDA board member, the associate chair, and the learning committee chair. During our presentation today, everybody is going to be muted. Please utilize the Q&A section to the right of your screen to ask the speaker any questions, which we will address after the presentation. I'd like to introduce you now to our speaker, Laurence Claus, with NNI Training and Consulting. Laurence is the president of NNI Training and Consulting and the director of Training and Education for IFI. He has more than 34 years of experience in the fastener industry, which includes positions such as vice president of engineering, general manager, new business development director, quality director, and engineering manager for a mid-sized fastener manufacturer. Laurence currently serves as chairman of the SAE Fastener Committee and the vice chairman of the ASTM F716 subcommittee. He is the author of numerous fastener articles and technical papers. Welcome, Laurence.
Thank you. Good afternoon, everybody. I hope you're all enjoying the NFDA virtual conference today. I hope that the sessions that have been before this one have been good and that you have been learning a lot. I was honored to be asked by the Industrial Fastener Institute and Fastener Training Institute to make this presentation at the NFDA conference on their behalf. So thank you to Kathy for the introduction. It's possible that many of you know me either directly or indirectly, either through an article that you may have seen in one of the fastener journals, or perhaps some industry training that you have attended in the past. I've been in the fastener game now for 34 years, and this subject that we're going to talk about today is one that always seems to garner a lot of attention. And I suspect that's because there's really so much to know about this particular topic. And unfortunately, we can't really do it a great deal of justice in 45 minutes. But I'm going to try to do my best to see that we make some good progress today. So today's presentation, I'm essentially going to broach on pretty much 4 different questions. Why do we plate and coat fasteners? What are some of the options of fasteners? And quite frankly, there are hundreds of, if not thousands of particular, variations and possibilities of things that we can coat and plate fasteners with. So I can't obviously hit on all those. So I'm only going to really tackle a number of the very common primary fasteners. We'll take a very brief look at each one of those. We'll address this question. I was asked when I put together this presentation to, again, try to weave the threads of, well, why do some platings cost this much or that much? And so I'll take a stab, certainly as I go through what some of the options are, but also as we get a little bit into this presentation, we'll look at some of the factors that, again, answer this question of why not all platings and coatings pretty much cost the same. And we'll conclude the presentation then with what appears to be out on the horizon. If you do have questions as we go along, again, I'm not, the way this format's set up, you're going to have to listen to me for the entire presentation. But if you have things, type them into your question and answer box as we go along, and we'll try to, hopefully we'll have enough time at the end that we can address everybody's questions. All right, so 4 reasons why we plate and coat fasteners. Now, quite frankly, there's far more than 4 reasons, but I want to focus on what I consider to be sort of the top 4. If we were going to be contestants on the game show Family Feud, if you've ever watched that show, you've heard Steve Harvey say, we surveyed 100 people and their top answers are on the board. And if we were playing that game show and this question came up, why do we plate and coat fasteners? I'd buzz in there and my answer would be corrosion protection. I'm sure that I would get the #1 answer for that. By far, the primary reason that we plate and coat fasteners is to protect them, to keep them from failing us in the applications that the customer has purchased to put them in. But some other reasons would be friction modification. And there's really sort of two aspects to this. One is simply you do have some customers who assemble parts and will occasionally have issues with things like galling or cross-threading or something like that. And having some friction modification might drastically reduce their possibility of having those problems. But more often, where we've seen a real rise in interest in friction modification in platings and coatings are for customers that do very high volume assembly and want to basically limit the erraticness of their assembly operations. They want to reduce the variation, the frictional variation in the torque tension relationship as they put fasteners in. All right, appearance is, is always a reason that people choose some of these platings or coatings. Anytime that a customer has a part that they have to basically put in view of their customers, they want that part to look good. They don't want it to look lousy or to be rusty or anything like that. So, appearance can often be a key reason why a customer would choose one plating or coating over another. And then identification. The example I have in this slide you see is actually a brake caliper. If you don't recognize that, if you don't work on cars or anything like that, you might not recognize that component. But that's an example of a brake caliper. That's the device that when you activate your brakes, when you push on your brake pedal, it basically, that's what squeezes the rotor to basically stop the wheel from turning. You can't see it in this picture, but that brake caliper basically slides, and it slides on those two colored pins, that silver left-hand pin and the gold right-hand pin. And when we look at those two pins, those are both basically cold-headed fasteners. And when we look at those parts from the front view, they look pretty much identical. Same size head, same shape of head, same type of flange or washer. And so if they looked identical to one another, there's really no way to distinguish, or not a really good way to distinguish between the two, because everything below the head might be completely different. And it might be very important to this brake manufacturer that, again, the one part, the left-hand part, get in the left-hand spot and the right-hand part get in the right-hand spot. So using plating in this case, they're able to easily change the coloring scheme on the parts to make it much easier to identify which one goes where. And I have all sorts of, I could spend a lot of time talking about all sorts of different types of examples of that. All right, so how do these platings and coatings work, or how are they intended to work? What basically drives them? And so there's four different types of primary protective mechanisms that the platings and coatings can fall into. The first one we'll look at there is what's called a barrier protective mechanism, or a barrier coating, sometimes it's referred to as. This is, as the word suggests, it's creating a barrier that blocks the corroding material from basically reaching the base metal. A good example of a barrier coating would be anything that is painted. Second one on the list, sacrificial, or sometimes will be referred to as galvanic mechanism. This is where the plating or coating basically sacrifices itself before the base metal will start to corrode. Zinc electroplating is a fine example of a sacrificial type of protective mechanism. Now, it works as long as there's zinc coating to sacrifice itself, but as soon as the zinc coating wears thin and starts to basically, expose areas of the base metal, then the part will start to corrode. So, actually any one of these mechanisms, once they are, if a barrier is interrupted, then it becomes vulnerable. The base metal becomes vulnerable. If a sacrificial one just sort of wears out over time. So most of these mechanisms are things that just sort of prolong parts' life. Protective oxides, the next one on the list. These are ones that create some kind of protective or inert layer on the top that protects the base metal below it from corroding. Stainless steel is a very good example of this. And then the last one on the list is perhaps one of the best mechanisms that we can employ. And in fact, it's not independent. And what I mean by that is the other three mechanisms above it could basically be, it could be a barrier coating or a sacrificial coating, but it could also have the characteristic that it is self-healing. So very often you see self-healing combined with one of these other three mechanisms. And what self-healing basically means is that if you damage it, it can repair itself. Just like us, if we walk through a bramble patch and we end up scratching, getting a scratch on our arm, we get a scab over that, and a couple days later, the skin's healed underneath it, the scab falls away, and we're completely back to normal. Same thing is true for self-healing mechanisms. And the finishes that, again, employ, at least as a constituent of their protective mechanism, self-healing mechanisms are the ones that are easily the best in the list as far as from a protectant standpoint. All right, there's lots of platings and coatings and finishes out there that we use on fasteners. This slide just gives you an idea of some of the general categories and some of the specific finishes then that fall in those general categories. But if we looked at all the different variations of each of these specific ones, if we looked at the ones that I don't have listed on this slide, we would see that there are just, again, hundreds, if not thousands of different combinations and variations of platings and coatings that can get employed on fasteners. We're gonna touch on most of these main, at least an example out of most of these main topics here in the next couple of slides. All right, so before I do that though, just a quick look at who is using what. And I'm assuming that my audience here, you all have sort of primary customers that that basically serve specific market interests. And so some of you may have, your business may be almost all automotive based. It might be a mix of automotive and industrial or defense work or so forth. So I'm just going to sort of show you sort of the main industry segments for fasteners, what some of the more common platings and coatings are. Now, granted, using automotive as an example, I've got 5 different ones listed under there. Again, those are the primary ones. We could probably make an argument that just about every type of finish perhaps gets employed somewhere in the automotive marketplace. So, these 5, it's not meant to limit the fact that other ones exist as well. So you can see in automotive, the primary coatings and platings are a couple of the zinc electroplatings, both the zinc and the zinc alloy electroplatings, the metal flake platings, phosphate coatings, and electrophoretic coatings, which is electrically applied paint, otherwise known as E-coat. In aerospace, you can see cadmium electroplate is a very common one, chrome nickel, anodizing of aluminum, and again, the use of specialty metals, protections of specialty metals like stainless steels and the nickel alloys. In a very similar vein, the defense industry uses many of those same general categories. Again, you see cadmium plating, and again, the specialty metals. The additions in the defense, though, is that and we'll talk about this a little bit later, is that they seem to be making greater headway in eliminating CAD or replacing CAD, and they seem to be doing that with zinc alloy electroplatings and metal flake electroplatings. On the industrial side here, again, industrial just covers a huge wide range of different options. So again, this is not all inclusive of every finish, but we do see a heavy concentration of zinc electroplating, metal flake platings, phosphate and black oxide coatings, and again, use of stainless steel in industrial applications. And then in construction, this is where we see hot dip galvanizing coming in as a popular choice. A lot of plain fasteners get used in construction simply because they're going to get painted. And so they don't necessarily need to have a finish put on them. In the residential construction area, we've seen a rise of ceramic and polymer coatings for things like deck screws and stuff like that. And then I included oil and gas. I guess oil and gas is sort of a mix. It's sort of maybe a subset of a little bit of construction, a little bit of industrial. And I included oil and gas because it is a significant industry pocket, and it has some unique plating and coating needs. And we see sort of a new entrant there, the Xylon coatings, which are Teflon coatings. We see a lot of that used in the oil and gas industry. All right, so let's move in and look again at some of these specific ones and see what, again, just learn a little bit about each one of these. I start out in the pole position with zinc electroplating, simply because it is by far the most commonly used plating or coating choice worldwide. I don't know, I've never seen an actual figure or, approximation of what part of the fastener market it uses zinc electroplating, but I would, in my own mind, my figures, I'd put it probably somewhere between 50 or 60% of the world's fasteners are zinc electroplated. So it is very, very commonly used. It's commonly used because, it has a number of advantages. It's cost effective, it's attractive, it supplies pretty good corrosion protection when you're using it in mild and moderate environments. Once you start to go to sort of moderate, severe, and severe service environments, zinc electroplating probably doesn't hold up anymore. But most applications are more in that mild to moderate range, so it's a good fit in those areas. Today, the natural colors are basically silver, yellow, and black. Sometimes the silver is called zinc in blue. If you're doing any business with customers that come from Europe, you probably have heard that term, zinc in blue. That's talking again about silver color. There's a definite bluish tinge to a zinc. We usually call it here in the US zinc and clear. So that sort of silver colored zinc often has a bluish tinge, and so sometimes it gets called zinc and blue. Again, a lot of advantages. I already ticked down a number of those, but it also, zinc electroplating also has its selection of limitations as well. Because of the nature, the chemistry of the way that the material basically deposits itself, if you have long, skinny parts, they become very vulnerable to heavy buildup at the ends of the part, which can then cause problems with thread gauging and things like that. So zinc electroplating, unfortunately, we might say, well, it has far less problems with fitting, parts together as, compared to something hot dip galvanizing, and yet it still can have that issue because of this issue of depositing efficiently and quickly on the ends of the parts. They're also subject to, high strength parts are subject to internal hydrogen embrittlement. I'm not going to talk about hydrogen embrittlement really much at all today, but hydrogen embrittlement is a failure mode that the fastener industry is deathly scared of. And we tend to assess as manufacturers and suppliers of fasteners, you tend to assess your risk of, how much risk does the part have for hydrogen embrittlement. And if it's a high strength part and you're using a zinc electroplating finish on it, it is at higher risk, susceptible to internal hydrogen embrittlement. When I talk high strength part, I'm talking about 180,000 PSI, or in the metric, the 1200 megapascal range. We're talking basically about socket head cap screws. Most fasteners fall below that. So most fasteners are in strength ranges that are, again, less than that and don't have a significant risk if you were to zinc electroplate them. There's a number of zinc alloy platings out there: zinc nickel, zinc cobalt, zinc tin, zinc iron. I'm only going to spend a minute focusing on zinc nickel. And the only reason I'm going to spend a moment on focusing on zinc nickel is it's getting a lot of play today. And it has for a number of years now. And the reason for that is that zinc nickel has been considered a replacement for cadmium for some time, and it seems to be that some of the recent studies that have been examining it, it seems to be one of the leading contenders for different electroplatings, at least, that would be a replacement for cadmium. And the reason for that, it has very similar electrical potential, which means that it's going to behave from a corrosion standpoint and so forth. It's going to behave very similarly to cadmium. And there are some versions of it that allow or basically have lower risk of hydrogen embrittlement than the zinc platings do. So it's sort of emerging, has been for a number of years. I don't want to make it sound like it's just emerging right now. It actually this has been developing over the last probably 10 years or so, but zinc nickel continues to gain an increase in interest for people that are looking at options for replacing cadmium. At the very bottom of the slide, if you just sort of turn your attention there, you can see that zinc nickel can actually be applied in several different fashions. And you'll see that there's some titles there: alkaline zinc nickel and acid zinc nickel. Now that's for that alkaline and acid are referring to terms related to the electrolyte bath or the plating bath that the plating is done in. And acid basically means that the pH of the bath is on the acidic side, and if it's alkaline, the pH of the bath is on the alkaline side. And there's arguments for for and against both of these basically processing methodologies. And so you might have a customer that's specifically looking for acid zinc nickel, and if that were the case, then you need to be very careful that you go to your applicators and make sure that the option that they are able to give you is acid zinc nickel. Because again, some applicators may do both. Some applicators may choose to do one over the other. And again, if you put your design cap on for a second, there are reasons why again, advantages to both. And so depending on what you want the part to do, you might choose one over the other. All right, phosphates, moving right along here. Phosphates are essentially crystals. They're somewhat unique in all these different options that I'm going to show, because unlike any of the other finishes, which actually basically deposit a noticeable thickness on the surface of the part, phosphates don't. Phosphates basically create what's called a conversion coating when you immerse them in a bath of heated phosphoric acid and phosphate salts. And the result is that you come out with this conversion coating on the top that is basically a set of crystals, crystal phosphates. And you see the pictures on this slide of those, of some examples of those crystals on the right-hand side. And this is illustrating the difference between small, medium, and large size crystals. And so when an applicator is basically validating that they have done this right, they're not measuring thickness, because you can't really measure thickness on this. They're measuring it by crystal size and weight. And so what you normally see on a print of a phosphate requirement would be something like grams per centimeters squared, or ounces per inch squared, or something like that. Some kind of measurement of weight over prescribed surface area. There's three types of common phosphates: zinc, manganese, and iron phosphate. Zinc phosphate is by and far the most commonly used on fasteners. Manganese phosphate is a very distant second. Phosphates, the biggest advantage of phosphates are that they, because of the crystal structure, you can see all those little fingers or all those little tendrils, they make it very advantageous. That's a very advantageous structure if you're going to put something like a paint or whatever over the top, because whatever you're putting over the top of the phosphate basically gets in around all those crystal fingers and gets held very tightly. So it's very good for adhering top coats, and it's used very much in that way. And so if a customer is thinking about painting a fastener, they might be inclined to purchase just a phosphated fastener, because the phosphate will help them with that painting afterwards. The other time that we see phosphates used with fasteners is where the part is not going to go into a very, severe or moderate duty application. You pretty much have to provide a little bit of corrosion protection, perhaps just enough corrosion protection to keep it from rusting from the time that the manufacturer has made the part to the time that the customer is assembling the part. And so with a little bit of oil or wax impregnated on top of the phosphate, it provides sort of enough shelf life to sort of provide that, that mechanism. And it's advantageous perhaps to use phosphates to do that over a zinc plating because it's perhaps cheaper. All right, black oxide, quick mention of this. Black oxide is an oxide that gets put on the part when you basically immerse it into a heated bath of a certain number of chemicals. The result is that you end up with this oxide called magnetite, Fe3O4, which provides a very deep, rich, very attractive black color. So if you're looking for a fastener that has a really attractive black that's not going to chip away and show what's underneath, black oxide might be a really good choice. Again, it gives you a nice black. It's not going to rub off. There's no hydrogen embrittlement risk. One of the other strong advantages of black oxide is it reduces light glare. It basically doesn't reflect. And so it's very commonly used in defense applications on, say, maybe like a stainless steel part or something where, a manufacturer of a tank doesn't want to have a nice shiny stainless steel fastener on the outside of the tank giving away the position of that tank. And so they might get black oxide coated, which will reduce or eliminate the potential for reflection. The limitations, though, are sort of like Henry Ford had with his Model T, and when he said that you can have it in any color as long as it's black. That's the case here. Black oxide only comes in black. So that's your only color option. And it doesn't have particularly good, again, a little bit like phosphates, it doesn't have really good corrosion protection. So you should only be using these in light or sort of light moderate duty applications. Anodizing is actually a reverse plating operation is almost we generally have to do some things to help it. And one of the things that we have to do is hold on a second. I understand are having some difficulties here with the, okay, it says, said we're good now on the thing. Sorry, it looks like we were freezing on my end, but hopefully that will stay stable now. All right, so passivating stainless steels, again, we want to make them even better than what they are in their, pretty much in their as-made condition. And so to do that, we, again, increase or boost the inertness of the oxide coating on the top of the parts. And that is done by passivation. Passivation means to make it more passive, more electrically inert. We do that in a heated bath. With fasteners, we do that generally in a heated bath of nitric acid or citric acid. Those are generally mild acid solutions. There are other acid solutions that you can do passivating in, but the majority of fasteners are done in these two things. The other thing that passivation does, other than really make the part more corrosion resistant by, again, making it more inert or reducing the electrical potential on it, it also cleans up any debris or whatever that has collected on the part. I'm sure that some of you could tell a story of, receiving a call from a customer at some point in time where they said, look, you told me you were selling me parts made of stainless steel and yet they're rusting. How can that be? Did you sell me something that isn't stainless steel? And you know that you made them out of stainless steel, so you're scratching your head. Okay, how are these parts rusting? Well, what happens is that stainless steel has an affinity for ferrite, free ferrite. And so if parts during the manufacturing process or during the processing of the parts are exposed to steel somewhere along the way. So let's say in the manufacturing process, they're collected in steel tubs and the part strikes the side of the tub. It's possible that some small particles of ferrite or iron basically slough off and attach themselves to the surface of the stainless steel. And once the part then gets out in its service environment or gets in an environment where it's a little bit moist or whatever, that little piece of iron rusts and you get these little rust spots forming on the surface. Passivation takes care of that. Passivation cleans all that sort of contamination off, and then by the process of, again, making it passive, more inert, it protects it from that happening again in the future. All right, metal flake coatings. These normally are identified by their trade name or their brand name. There are about 4 or 5 different companies that are sort of predominantly working in this space. When we talk about a metal flake coating, and sometimes they're actually also referred to as dip spin coatings. And as you'll see in a minute when I talk about how they're applied, that's how they get their name. That's the description of how they get applied. But however you are familiar with hearing about these are, again, a distinct family of parts and or of coatings. They essentially take a metal, usually zinc or aluminum. They take very fine sintered powder or flakes of that metal, and they mix it or embed it they mix it and embed it in the that base matrix is very much like paint, and so essentially the coating gets put on and gets dipped into this paint-like material. It then gets pulled out. It gets spun. So all the excess gets spun off. It gets dropped onto a conveyor belt, taken into normally an oven or furnace that cures the part, and then that process normally iterates several times. And so there's normally, it's an iterative process. These are normally multi-layered finishes, which means that they are relatively thick. But they've gained a lot of interest in today's market because they hold up quite well to protection, to protecting against corrosion. They routinely achieve 1,000 or more salt spray hours. Talk about a couple of forms of galvanizing. We have a term called mechanical galvanizing. Some people may refer to it as mechanical plating. It probably depends on the size and type of part, maybe the segment of the industry that you're working in, whether you call it mechanical galvanizing or mechanical plating. But this is a process where a metal is applied to the surface of the part mechanically, meaning that it is essentially pounded into place, as opposed to the electrochemical process that we see in electroplating. It's capable for zinc, tin, aluminum, copper, cadmium, perhaps some other metals as well, but the common ones would be zinc and perhaps tin. Let me just say here, and again, because this is a very condensed presentation, I'm not really spending time here pros and cons on most of these different applications. But I do want to say this: if you look at the picture, if you have good imagery on your screen, you look at the picture in the upper right corner, you can see that the picture of these parts, which are which are mechanical zinc plating, are relatively dull in color. And if you can look closely, they almost look gritty. The surface looks sort of gritty. That's very common in mechanical plating. They're very, very different than electroplated parts. And so if you have a customer that has been perhaps purchasing a electroplated zinc part from you for many years, and then decides, because they want to, say, reduce their risk of hydrogen embrittlement, so they want to mechanically plate the parts, they ask you to do that, then you got to educate them a little bit, because the appearance is so different. For all practical purposes, these are they're completely different animals than the electroplated zincs, and there's really very little comparison between the two, other than in name. They both are zinc platings. They perform very differently and have very different characteristics. Okay, hot dip galvanizing then is the process where you are immersing steel parts into a molten zinc bath. The temperature of the zinc pretty much reacts with the steel to create a distinctive zinc iron alloy at that interface, and then subsequent zinc that gets that builds up on top of that has some different type of structures and so forth. But you end up with generally very thick coatings. You can see down there 43 to 86 microns. So generally thick and a lot of variation in them. That creates problems for users some of the time because of fitment issues. They can't get a nut and the bolt to fit together easily. But the one thing about hot dip galvanizing is this is probably the only coating or finish that I'm aware of that really has a lot of historical data to support what it does. And so it's very predictable because there's a lot of long-term historical data that will tell us what parts that are hot dip galvanized will do. By the way, I've skipped past the middle bullet point there, but one of the other advantages of hot dip galvanizing is that once the part is actually put into service, so once that part is actually exposed to the atmosphere out there, it reacts with the oxygen and carbon dioxide in the air to form zinc oxides and zinc carbonates, and those actually boost the corrosion protection. If fitment is an issue, but again, hot dip galvanized type of structure is interesting to you, there are several alternatives which provide slightly less thick finishes. One is called high temperature galvanizing, goes by the name Delta galvanizing. It's not used much here in the United States. It uses a molten zinc bath that's higher temperature than the standard hot dip galvanizing. And the process that is here in the US that you would find more commonly in the US is thermal diffusion galvanizing, otherwise known as shearodizing. And this is done, this isn't dipping the part in a molten bath at all. It's done in a chamber with basically a special processing chamber where they add zinc powder in, and it's thermally diffused onto the surface. Xylon, I think this is my last slide here. Xylon is, again, an interesting coating for anybody that is doing work in the oil and gas industries. It's a Teflon coating. Xylon is essentially the same material that makes up nonstick cookware. And so it's very good from a lubricity standpoint, but also has excellent corrosion and chemical resistance. And it's, again, highly favored in the oil and gas industry. All right, a quick, and I really only have one slide here on the cost, but a quick thing to say about costs. So I like this quote that Benjamin Franklin once made. He said, the bitterness of The bitterness of poor quality remains long after the sweetness of low prices are forgotten. It's really important when we're talking about platings and coatings that we are choosing platings and coatings based on the solution, based on providing a solution to the customer's needs. If the customer tells you, that they want the absolute cheapest thing in the world, then there's some options out there for you. But we don't want to be driven. If they tell you, I've got all these needs, it needs to do this, it needs to do this, it needs to do this. Oh, and by the way, I don't want to pay very much for it. You need to focus on finding a finish at whatever cost it's going to take to accomplish those needs. Because if you choose a low cost version first, you probably are going to not meet the customer's needs. So what factors affect the cost? All right, so we can go down this list here in order. Raw materials, example here to illustrate this, gold plating is obviously going to be much more expensive than zinc plating. Gold is a very expensive material, and zinc is a relatively inexpensive material. Coating thickness, sort of comparing zinc finishes along the spectrum. A commercial, what we call a commercial zinc, which are a flash zinc, which is just a very thin coating of zinc, versus say a 13 micron coating of electroplated zinc, which is a relatively heavy or thick coating. It takes more time to get the heavier coatings. It takes more material. So again, there's going to be an impact on the cost. Heavier the coating, or the more thickness of the coating, probably the more expensive the part's going to be. Process. Using an example here of the metal flake finishes, there are several different ways that metal flakes can be applied. Dip spin, that's the standard method. That's relatively cost effective. But let's say that a customer said, I really want this part to look really good. You could spray it. You could spray it on. And that is a viable process, but it's, again, a much more expensive process. Availability. Is your applicator around the corner from you, or basically in your region, or do you have to ship it several states over? Obviously, if you have to ship it a long way and ship it back, there's transportation costs and there's time costs associated with all those sorts of things. Efficiency, does this plating allow for efficient plating or not? Zinc electroplating is commonly done in 48-inch or 60-inch barrels at some commercial electroplaters. You're going to, obviously, it's going to be much cheaper to process a large batch of parts in a 48-inch barrel than it is in a 12-inch barrel. And then environmental concerns. Environmental concerns are not always necessarily with the finish on there as much as perhaps maybe what's left over from the process. What kind of waste is created that the applicator has to manage. All right, so that brings us into the home stretch here. And I have a couple slides here that I have titled sort of stay tuned, topics to watch for. And as I go through these, some of you are going to be scratching your head. You're going to be saying, Laurence, there's nothing new here. Why are you talking about these? These things aren't new. And I want to stress the fact that that is true to one degree, but these are all things that I'm identifying that you need to make sure your radar is attuned to, because there are things happening in our industry related to these things. And you need to make sure that something doesn't get dropped in on you by surprise that's going to change things. So let me cover these again briefly. We'll start with cadmium replacement. Again, for some of you, you're scratching your head because you predominantly support the automotive industry, and you're saying cadmium's been gone for 30 years, and you're absolutely right. Cadmium's gone. It's never coming back. It's not even a discussion we're ever going to have again in automotive. But it's still a very active topic in aerospace and defense. So if you are supplying parts in those arenas, cadmium replacement is still a hot topic. There's a recent study done by the Army. Now I'm going to do recent is in quotation marks, because recent probably is about perhaps almost 8-10 years ago. But again, a lot of these folks that have been heavy users of cadmium are trying to find alternatives to using cadmium. And the Army undertook a pretty comprehensive study a number of years back to try to find alternatives to cadmium finishes. And they finished that. They basically identified zinc nickel and the metal flake finishes. And we're starting to see some of that now starting to accelerate. I was recently told that SAE either has come out or is about to come out with a standard, not out of the Fastener committee, by the way, but I think it's out of the aerospace, one of the aerospace committees, but that SAE is about to come out with a standard for zinc nickel. That again is a direct reflection of this Army study that was done. Hexavalent chromium, again, 15 years ago. This goes back 15 years, and you're saying, you know, we had to deal with this 15 years ago, Laurence. What's the issue now? Well, the issue with that, again, hexavalent chrome is one of two of the ionic states of chromium. It is the more aggressive of the states. It's been proven to be dangerous to people and dangerous to the environment. And so about 15 years ago, the European Union passed a law called the Directive on End-of-Life Vehicles, which is about recycling cars. And if you're saying now, okay, what does recycling cars have to do with, what does recycling cars have to do with hexavalent chrome? Basically, they said you can't recycle cars if there's hazardous stuff in them. So we're gonna ban some of these materials that are hazardous materials. And hexavalent chrome was one of those things. They put a timeline of several years that you had to get hexavalent chromium off of or out of the cars. And that forced the US to pretty much get it out of our automotive industry. The fact that the automotive industry the automotive industry was pretty much has a lot of influence. So it ended up resulting in the industry here pretty much having to go across the board. In other words, the surface finish industry across the board had to find ways to eliminate hexavalent chromium. The thing here, although it was 15 years ago, eliminating hexavalent chromium does some really good things. I mean, it really has some good performance capabilities, and the alternatives weren't as good. And so for the last 12 to 15 years, the surface finishing industry has continued to try to basically make up for lost ground that they lost 15 years ago when hexavalent chromium was eliminated. So we continue to see improvements in chromates and post-plating operations and so forth to address that particular issue. The other thing that I think, again, we just need to keep an ear open about is that at the time that hexavalent chromium was being eliminated, people were asking the questions, or the discussion was out there, well, what about trivalent chrome? We really ought to just be designing without chrome at all. And that I haven't heard that discussion in a long time, certainly in a number of years. But with the new governmental administration that is perhaps more interested in in environmental affairs, it's not out of the realm of possibility that these sorts of discussions might come up again. And so just need to, again, keep your ears open about that stuff. Regulations, nothing on this list is new. The newest on this list is the very last one, California Proposition 65, which basically had a revision a couple of years ago, and it's a labeling regulation. So again, nothing really new to report here, but the reality is that none of these regulations are going away. And over time, what happens is they evolve over time. And so just as whenever these things came out and your businesses had to address the issues related to some of these issues, if there is a revision to any of these, you may end up having to redo that. Rojas has had several revisions already. And so again, you can't say we've addressed it and then just totally forget about it. Again, keep these things in your, on your radar screen, because they do periodically change. All right, we're getting close here. Changing customer requirements. Customers are always raising the high bar. We will continue to see customers that want improved corrosion requirements. Perhaps some of them will want to be eliminating chrome products. That will definitely be true if there is a a rebirth of discussion about eliminating chrome products because of the environmental issues. We see changing accelerated corrosion test methods, adding new platings and coating standards. All those things are things that customers influence and we need to be on the lookout for. Changing industry standards. Pretty much every finish that's applied to a fastener is being applied pursuant to some type of standard. Some of those standards are what we call consensus standard organization standards. Some of those standards are company standards. But if it's a consensus standard, so it's like ASTM or ISO, those standards get reviewed, not revised necessarily, but get looked at every 5 years. And if it's a standard that basically has things that sort of time out, or it's very highly used, or there's a lot of new information about the contents of that standard, those sorts of standards will get revised somewhere in that 5-year time period. And so as an example, ASTM F1941, F1941M, and ISO 4042, those are both fastener standards for electroplating. Both of those standards have undergone relatively recent significant changes in the last couple of years. We're also going to see, I'm predicting that we will see a sort of a rebirth or new discussions about the hydrogen embrittlement requirements in standards. Salim Brahimi, who's the technical director at the IFI and pretty much the world expert on hydrogen embrittlement, has spent a good part of his career forming and working at the McGill University Hydrogen Embrittlement Center, and they have developed all sorts of new understanding about hydrogen embrittlement in fasteners, and that information is now slowly getting input into standards. And so I think we'll see continued increase there. And then finally, some innovations that are going on in the surface finishing industry, improved torque tension options. There's more and more work being done there. They continue to improve the dip spin processing technologies to eliminate some of the limitations that come out of that methodology. Tin and tin zinc, I think we'll see a greater interest in use in those finishes as more and more electric vehicles in particular start to hit the roads. Those finishes are excellent for electrical connections. Zinc nickel, as I said, appears to landed as the winner for CAD replacement, and metal flake finishes are getting thinner, but actually increasing salt spray hours. Another one, I was just reminded of it from Kelly before this session, but there are now some chromates being released by some of the chemical manufacturers that are potentially allowing for baking after chromating as opposed to before chromating. Traditionally, you have always baked before chromating because the heat of baking destroys or damages the effectivity of the chromate finish. And now it seems they've come out with some options, perhaps with you don't need to take them out of the process. You can do it after the process is completed. All right, so before I get to questions, just two real quick reminders about some upcoming events. If you are interested in any kind of training, I would ask that you consider these two things. The IFI will be conducting its next training session on March 16th. It'll be Lessons in Using Fastener Standards. It's a virtual 2-hour training. You can find more information about it there at the Industrial Fastener Institute's website, or actually at the Fastener Training Institute's website. And the other one on here, and I just want to really highlight this one, is that Fastener Training Institute is offering the Fastener Training Week in Houston about 3 weeks from now, March 22nd through 25th. This will be the first time in a year that it has been done in person. This is a very intense, in this case, it's normally it's 5 days because of COVID things. It's actually, this one will be 4 days, but it's an intense learning situation. If you are new to the industry, if you've been around the industry for a while, but you want to learn more about fasteners and fastener engineering, this is a really tremendous opportunity for you, and I highly recommend folks look into it. Again, you can find more information about it on the Fastener Training Institute's website. All right, so with that, we have gone to the end, and I've got about 5 minutes, so I'm not sure we'll get to all the questions, but we're going to take a stab at them. Kelly, did you want to get on, or have you been putting them in the chat for me?
They're in the chat. I'll go ahead and read them off to you if you like.
Okay.
Do you know of a good resource or anything like a compatibility chart for bimetallic or dissimilar metal corrosion when combining different coatings or coating reactivity with different grip metals?
Do you know of a good resource or anything like compatibility chart for bimetallic or dissimilar? So there is a galvanic table that basically will show that table will show metals that that are basically of similar compatibility, as well as basically point out the ones that are not real good capability. So I know the person that asked this question, if he wants to get to me separately, I could send him a copy of that chart. But if you're not that individual and you just want, and this is an interesting question to you, you could Google galvanic series table, and it will show you all the different materials sort of in order, and it'll bunch them by ones that you can, again, sort of by families or similar potentials that you could. Again, they may be dissimilar metals, but in fact, you can put them together.
All right. And what is the timing to the change in hydrogen embrittlement industry specs? My understanding is that the baking duration will increase. Can you confirm this is the case and the timing associated with this change and perhaps cost implications?
So the timing to change hydrogen embrittlement industry specs, long time. I would consider it to be a long time. It will start at the CSO level. So we'll start with organizations like ASTM and so forth. They'll get into their standards first, and then it will be slowly adopted by other people that use basically the ISO and the ASTM standards as their sort of foundation plate. So that process is a slow process. It'll take quite some time, I think. The question is, one of the major changes is, yes, there is one of the understandings is that the historic rule of 4, 4, and 4, meaning that you plate the part, or excuse me, you bake the parts for 4 hours, has been found to be insufficient. And so the baking times very likely could go to maybe 3 times that or so. And these standards, again, may very well increase those as we go forward. What are the implications of that? There certainly are cost implications of that. The longer you have to bake, obviously, the more it's going to cost to do that process. It also, the longer bakes create real sort of logistics bottlenecks for the applicators, because they have to juggle everything right. If they have jobs that have to go into the furnaces, once they get parts in the furnace, they can't be opening that door back and forth. So they have to have enough furnaces to be able to manage their flow.
And what is the general standard for acceptance of thread pitch after plate with some of these dip spin coatings? Should threads be produced undersized to allow for these thicker coatings?
All right, that's a much longer question than I can answer in 1 minute. We've got 1 minute left. But I will just say on that you have to work with the manufacturer on that, certainly, and the applicator. And they can be produced without having to undersize, but that's not always true. And so that's going to be sort of a fine dance that the applicator and manufacturer are going to have to work through.
Okay.
I think we're out of time.
We are. So Laurence, I'd like to thank you for the presentation. And I'd like to invite everyone to join us for the next session, the Logistics and Supply Chain Challenges panel discussion. Thank you very much.
Thank you.